Hi everyone, this video is on statistics and more specifically on z-scores and bell-shaped curves. So z-scores are a way of comparing data from different data sets. So for example, if we had two exams, a maths exam and an English exam, and let's say we scored 78% on a maths exam and 70% on an English exam. Now, just looking at raw data, we can assume, or we can see, or we can state that we achieved a better mark on the maths exam. But when we look a bit deeper, it might not be that clear cut. So for example, if the mean of the maths exams was 80% and the mean of the English exams was 65%, then we can now see that perhaps the English exam is a better result compared to the rest of the people doing the exam than the maths result. And this could be because the maths exam was a bit easy or easier than the English exam, or it could be that the people that you're competing against were better. But there's reasons why in this case as to why a score might be the way it is. If we have a different mean though, if we have a mean of say 73%, then now it's not as clear cut. We could maybe say it's about equal between maths and English, because in both instances the score that we achieved is below the average and slightly below the average. So now we're not so sure. If we delve a little bit deeper and have a look at the standard deviation of each of the topics, so let's say the standard deviation of maths is 1.4 and the standard deviation of English is 4.7. So now we can see that perhaps the English exam was a better mark because you are less than one standard deviation away from the average with the English exam, whereas the maths mark was more than one standard deviation away from the mean and below the mean. So in both subjects, the exam mark was less than the average, but relative to the standard deviation, which again is a measure of how spread out the data is, the English exam is closer in terms of standard deviations to the mean than the maths mark. Even though the English exam is further away from a raw score perspective, maths is 2 marks away, whereas English is 3 marks away. Maths is further away when comparing it with the standard deviation. So all of that analysis that we just did, that's what z-scores do. Z-scores give us a value that summarizes all that information that we just talked about. So the formula for a z-score is z equals x minus the mean over the standard deviation. And x represents the raw data score. The x with a bar is the mean of x, and that's the standard deviation of x. And so if we do the analysis for both of the topics up the top, we can work out the z-score for each. So maths, the z-score would be 78 minus 80 over 1.4, and English, the z-score would be 70 minus 73 over 4.7. And we can just do that on the calculator. So the first one, 78 minus 80 over 1.4 is negative 1.43. And the next one, 70 minus 73 over 4.7 is negative 0.64. So now we can be even more specific or even more accurate than we were in the beginning. We knew that maths was less than one standard deviation below the mean. More than one standard deviation below the mean, and we knew that English was less than one standard deviation below the mean, but now we know exactly how many standard deviations below the mean it is. So maths is 1.43 standard deviations below the mean, and English is 0.64 standard deviations below the mean. So the fact that our z-score is negative means that it's below the mean, and the value of the z-score says how many standard deviations it is either above or below. So if we think of another, let's say we had a science exam and our z-score was 1.6. What this means is that our score was 1.6, let's make that a little bit clearer, 1.6 standard deviations above the mean. In this case it's above because it's positive, and it's 1.6 standard deviations above the mean for that subject. Now we don't know what the score was, we don't know what the average was, and we don't know what the standard deviation was. But according to our z-score, we know that it was above the mean by 1.6 standard deviations. So z-scores allow us to compare what's going on between data sets that aren't comparable. They're not the same data, they're different data sets, but z-scores are our comparison between them. Now, this formula can be used obviously to find z, like we just did then, but it can also be used to find one of these variables as well. So out of these 4 variables, they'll always give you 3 of them and then ask you to find one of them, either just the z-score or one of these in the actual formula, in which case you can use solve on your calculator. So that's what z-scores are. It's that comparison tool, and it allows us to compare. Now, we're also going to look at normal distributions. And normal distributions can be called that, or it can say that data is normally distributed, or it can talk about a bell-shaped curve. Now, a bell-shaped curve is this, and it replicates what the big church bells look like when they sort of look like this, with the little dongle down the bottom that would ding. That's the shape of a bell, and that's why these are called bell-shaped curves, because they look like that. So with a bell-shaped curve, what we know, because it's symmetrical, is the mean is in the middle. Now, it's the same value as the median when data is balanced or symmetrical, but with bell-shaped curves, we deal with the mean. And then we look at standard deviations. So what we know is that if we go 1 standard deviation to the left, so let's call this x bar, that'll be x bar minus 1 standard deviation. And then we go 1 standard deviation to the right, so x bar plus a standard deviation. We know that in between those values is 68% of the data. 68% of the data lies within 1 standard deviation of the mean. If we go another standard deviation either side, so that's 2 standard deviations to the left and 2 standard deviations to the right, we know that's 95% of data. And if we go another standard deviation to the left, so the mean minus 3 standard deviations and the mean plus 3 standard deviations, that's 99.7% of data. So these percentages never change. And these are estimates. You can look this up and get more accurate measurements, but for the sake of this course, we use these values. So 68, 95, 99.7%. You might often hear this called the 68, 95, 99.7% rule, and that's because of what those percentages are. So what we then can do is we can use this information for any data that is bell-shaped. So the most commonly used normal distribution is IQ tests. Now IQ tests, we know, are bell-shaped with a mean of 100 and a standard deviation of 15. And that's true for all IQ tests. So the average score on an IQ test is 100, and then what we can do is do 15 either side, 15 either side of that, and 15 either side of that. Now, with these percentages, we can actually summarize this information by working out the percentage of each section. So if that's 68% in total, then it must be 34% either side. This is 13.5% either side, 2.35% either side, and 0.15% either side. Now those percentages don't change. They are true for every single normal distribution that you can be asked to think about. These values down here, on the other hand, they change. They are specific to the question that is being asked. So as soon as you know a situation is normally distributed, these percentages can all be written in because that doesn't change, but these values down here, they are specific to the question. So once you've done this, we can then answer questions such as, find the percentage of people with an IQ between 70 and 145. So what we do is we pinpoint where 70 is and where 145 is, and then we just add up the percentages that is encompassed in that. So that would be 97.35%. So that's the basic level of a question that can be asked. So you've drawn your bell shape and then you're just counting up percentages. What tends to happen in the exams, they then go a step further, which is then they do a follow-up question where they give you a specific amount of things. So for instance, they might say, there's 500 people, a group of 500 people. How many have an IQ between, let's say, 100 and 130? So we'd go to our bell-shaped curve, we'd find where 100 is and where 130 is, and we'd add up those percentages. So in this case, that's 47.5%. And we have to work out what 47.5% is of 500. And if you're wondering how to do that, percent means divided by 100, of means times, and we just calculate that. So that would be 237.5. And then we just round it, so it'd be 238. So hopefully that makes sense. That's what the questions will ask you to do. Now, there is one more connection that I'd like you to know, and that is with the bell-shaped curve. So we'll go back to, let's do this one, and we'll choose black. If we're relating z-scores to bell-shaped curves, remember the z-score tells us how many standard deviations a score is above or below the mean. Now remember, this is one standard deviation above the mean. So this score here actually relates to a z-score of 1, and this is a z-score of 2 and 3, because it's 1, 2 or 3 standard deviations above the mean. This score here is -1 standard deviations, -2, -3, because that's 1, 2 or 3 standard deviations below the mean. Now the mean is 0 standard deviations away from the mean, so we put a 0 there. So we can actually relate the z-scores and the bell-shaped curves, and I'll do that again. So the mean and has a z-score of 0. 1 standard deviation to the left has a z-score of -1, -2, -3, 1, 2, 3. So they're the z-scores as they relate to the bell-shaped curve. So your job now is to find lots of questions on this stuff and obviously consolidate and get better at it. And if you need any help, please let me know.